Imagine you wake up tonight and the moon is gone. Not obscured by clouds, not below the horizon. Gone. The sky is clear, the stars are out, and the place where the moon should be is simply dark sky. Nothing. In the first hours, the change is mostly aesthetic. The night is darker than you have ever experienced. Not because anything has happened to the stars, but because you have spent your entire life in a world where the moon provided a significant fraction of nighttime illumination, and now it does not. The nights are darker. The stars are brighter, paradoxically, because the sky background is darker. Animals that navigate by moonlight are disoriented. Tidal rhythms that have governed the behavior of coastal organisms for hundreds of millions of years are interrupted. In the first days, the tides change. The moon is responsible for approximately 2/3 of Earth's tidal forcing. The sun contributes the remaining third. Without the moon, the tides do not stop. The sun's gravity still pulls on Earth's oceans, but they are dramatically reduced. The tidal range, the difference between high tide and low tide, drops by approximately 2/3. Coastal ecosystems that depend on the intertidal zone, the strip of coastline exposed and submerged by tides, are immediately stressed. Organisms that time their feeding, reproduction, and behavior to the tidal cycle face a sudden and permanent change in the environment they evolved for. In the first months, the length of the day begins to change. The moon's tidal interaction with Earth has been slowing Earth's rotation for 4.5 billion years. Without the moon, this braking force disappears. Earth's rotation rate, currently slowing by approximately 1.4 milliseconds per century, stabilizes. The day is no longer getting longer, but the days are already shorter than they would be if the moon had never existed. Earth's rotation has been slowed by 4.5 billion years of lunar tidal braking. Without the moon from the beginning, Earth's day would currently be approximately 6 to 8 hours long, rather than 24. Removing the moon tonight does not restore the 6-hour day. That energy has already been transferred. Earth's current 24-hour rotation rate is what it is, and the moon's absence going forward means it stops changing, not that it reverts. In the first centuries, nothing dramatic happens. Earth continues to orbit the sun. The seasons continue. Life continues. The effects of the moon's absence are real, but slow. In the first tens of thousands of years, something more significant begins. Earth's axial tilt starts to drift. This is the change that most people do not think about when they imagine removing the moon. And it is the change that, on geological timescales, has the most profound consequences for life on Earth. In this video, we are going to go through all of it: the immediate effects, the medium-term effects, and the long-term effects of a world without the moon, including the one consequence that most people overlook and that most planetary scientists consider the most important. Stay with me. Before we go further, the moon is currently moving away from Earth at approximately 3.8 centimeters per year. In 4.5 billion years, it will be far enough away that it no longer covers the sun during solar eclipses. Total solar eclipses will no longer be possible. Drop a comment if you knew the moon was leaving. And drop a comment if that changes how you feel about the next total solar eclipse visible from your location. Let's start with what changes immediately, within hours and days of the moon's disappearance: the tides. Earth's tides are produced by the differential gravitational pull of the moon across Earth's diameter. The side of Earth facing the moon is pulled more strongly toward the moon than Earth's center, and Earth's center is pulled more strongly than the far side. This differential creates a stretching force, a tidal force, that elongates Earth's oceans into an ellipsoidal shape aligned with the moon. As Earth rotates, different parts of the ocean move into and out of this tidal bulge, producing the characteristic rise and fall of sea level that we call the tides. The magnitude of the tidal force depends on the mass of the moon and the inverse cube of the distance to the moon. The tidal force falls off more rapidly with distance than gravity itself. The sun also produces tidal forces on Earth, but despite the sun's vastly greater mass, it is much further away. And because tidal force falls off as the inverse cube of distance rather than the inverse square, the sun's tidal effect is only approximately 46% of the moon's. When the sun and moon are aligned, at new moon and full moon, their tidal forces add together, producing the large tides called spring tides. When they are perpendicular, at first and third quarter, they partially cancel, producing the smaller neap tides. Remove the moon, and only the solar tides remain. The tidal range, the difference between high and low tide, drops to approximately 46% of the current spring tide range, and approximately the same as current neap tides everywhere and always. This sounds manageable, but the intertidal zone, the coastal strip that is alternately covered and exposed by tides, is one of the most biologically productive environments on Earth. It supports a unique community of organisms: barnacles, mussels, sea stars, anemones, shore crabs, that are specifically adapted to the alternating wet and dry conditions of regular tidal flooding and exposure. The intertidal zone's character depends critically on tidal range. The width of the intertidal zone, how far up and down the slope the tides reach, determines how much habitat is available. The frequency and duration of exposure determine which organisms can survive there. Without the moon, the intertidal zone shrinks to approximately 46% of its current extent in tidal range terms. The upper intertidal, the zone that is currently exposed for long periods during neap tides, and the upper part of spring tides, becomes permanently submerged. The lower intertidal, currently submerged most of the time, becomes the dominant zone. Organisms specifically adapted to the upper intertidal, organisms that require periods of aerial exposure to feed, to reproduce, or to avoid predators, lose their habitat. The ecological restructuring of coastal ecosystems begins immediately and proceeds over years to decades as species either adapt, migrate, or go locally extinct. The salmon, the horseshoe crab, the sea turtle, all organisms whose reproduction is timed to tidal cycles face an altered environment within the first tidal cycle after the moon's disappearance. The timing of spawning that evolved over millions of years of lunar tidal synchronization becomes misaligned with the new sun-only tidal rhythm. Beyond the direct ecological effects, the reduction in tidal mixing has oceanographic consequences. Tides play a role in mixing the deep ocean, bringing nutrient-rich deep water to the surface and oxygenating deep water from the surface. The reduction of tidal mixing affects ocean circulation patterns, nutrient distribution, and ultimately ocean productivity on timescales of years to centuries. The relative contributions of the moon and sun to Earth's tides were quantified by George Darwin, Charles Darwin's son, in the 19th century using his theory of tidal evolution. The moon's tidal force at Earth's surface is approximately 2.2 times that of the sun, meaning the moon contributes approximately 69% of total tidal forcing, not 2/3 as sometimes stated. The exact ratio depends on the current positions of moon and sun. The tidal braking of Earth's rotation by the moon transfers angular momentum from Earth's spin to the moon's orbit, causing Earth to slow and the moon to recede. This process has been ongoing for 4.5 billion years and is directly measured by lunar laser ranging experiments using reflectors placed on the moon by Apollo astronauts. To understand what losing the moon means for Earth's rotation, you need to understand what the moon has already done to Earth's rotation over 4.5 billion years. When the moon formed, approximately 4.5 billion years ago, in the giant impact event in which a Mars-sized body called Theia struck the proto-Earth and the debris coalesced into the moon, Earth's rotation was much faster than it is today. Estimates based on the angular momentum of the Earth-Moon system suggest Earth's initial rotation period was approximately 5 to 6 hours. Over 4.5 billion years of lunar tidal breaking, Earth's rotation has slowed from approximately 5 to 6 hours to the current 24 hours. The day has lengthened by approximately 18 to 19 hours over 4.5 billion years, approximately 1.4 milliseconds per century on average, though the rate has varied significantly over geological time. This slowing has a direct consequence for life. A faster rotating Earth has stronger Coriolis forces, the pseudo-forces that arise from Earth's rotation and that drive the large-scale circulation patterns of the atmosphere and oceans. A 6-hour Earth would have much stronger Coriolis forces than a 24-hour Earth. Stronger Coriolis forces drive faster and more energetic atmospheric circulation. The jet streams, the high-altitude wind systems that drive mid-latitude weather, would be faster and more vigorous. The Hadley cells, the tropical circulation systems that drive trade winds and monsoons, would be narrower and more intense. The general character of Earth's climate system would be different. Some researchers argue that the slowing of Earth's rotation by the Moon has contributed to Earth's relatively moderate climate, that a faster rotating Earth would have more violent weather systems, potentially less stable climate, and possibly less favorable conditions for the development of complex life. This is speculative. We do not have a planet with 6-hour days to compare to, but the physics of the relationship between rotation rate and atmospheric dynamics is well established. When you remove the Moon, the breaking stops. Earth's current 24-hour day freezes in place. It will not get longer. The Moon is no longer there to transfer angular momentum from Earth's spin to the Moon's orbit. But it will also not revert to a shorter day. The angular momentum that was already transferred is gone. So the immediate effect on rotation rate is nothing. The day stays at 24 hours. The long-term effect on rotation rate, also nothing. The day stays at 24 hours forever, or until some other tidal mechanism, the sun's much weaker tidal breaking, very slowly continues to lengthen the day over billions of years. This is perhaps the least dramatic consequence of losing the Moon, but understanding it sets up the most important consequence, the one that operates over tens of thousands of years. The history of Earth's rotation rate has been reconstructed from geological records in tidal rhythmites, sedimentary layers deposited by ancient tidal cycles that preserve a record of tidal period, and hence Earth's rotation rate at the time of deposition. A study by Williams, 2000, of Precambrian tidal rhythmites from South Australia, dated to approximately 620 million years ago, found evidence of approximately 400 days per year, implying a day length of approximately 21.9 hours at that time. Even older records, from approximately 900 million years ago, suggest approximately 18-hour days. The extrapolation to the initial Earth-Moon system gives approximately 5 to 6 hour days at formation. Here's the consequence that most people overlook, the one that planetary scientists consider the most important contribution of the Moon to Earth's habitability. Earth's axial tilt, the angle between Earth's rotation axis and the perpendicular to its orbital plane, is currently approximately 23.5 degrees. This tilt is responsible for Earth's seasons. The northern hemisphere is tilted toward the sun in June, receiving more solar radiation per unit area and experiencing summer. It is tilted away in December, receiving less radiation per unit area and experiencing winter. Without axial tilt, there would be no seasons. The equator would be perpetually warm, the poles perpetually cold, and the mid-latitudes would have an intermediate but constant climate throughout the year. With axial tilt, there are seasons. The distribution of solar energy across the surface changes throughout the year, driving the large-scale atmospheric and oceanic circulation patterns that make Earth's climate what it is. 23.5 degrees of axial tilt is not a fixed value. It varies. Over cycles of approximately 41,000 years, the obliquity cycle, Earth's axial tilt oscillates between approximately 22.1 degrees and 24.5 degrees. This variation is caused by the gravitational perturbations of the other planets, primarily Jupiter and Saturn, on Earth's orbital plane. The Moon stabilizes this variation. The Moon's gravitational influence on Earth's equatorial bulge, the slight flattening of Earth's shape at the equator caused by its rotation, provides a restoring torque that resists changes in the axial tilt. The Moon acts as a stabilizer, keeping the axial tilt within the relatively narrow range of 22.1 to 24.5 degrees, despite the perturbations from the other planets. Without the Moon, Earth's axial tilt is not stabilized. Simulations of Earth's rotational dynamics without the Moon, most notably by Jacques Lascar and colleagues at the Paris Observatory, published in Nature in 1993, show that without the Moon's stabilizing influence, Earth's axial tilt would vary chaotically between approximately 0 and 85 degrees over timescales of tens of millions of years. 0 to 85 degrees of axial tilt. At 0 degrees, there are no seasons. The poles are permanently cold and dark, the equator permanently warm. The climate is stratified by latitude with no seasonal variation, a fundamentally different climate system from today's. At 85 degrees, Earth is essentially lying on its side. The poles point nearly directly at the sun for half the year and directly away for the other half. The polar regions experience continuous daylight in summer, a sun that circles the sky rather than rising and setting, and continuous darkness in winter. The equatorial regions experience rapid day-night cycles throughout the year. The seasonal variation is extreme and unlike anything in the current climate system. The Lasker simulation suggests that without the Moon, Earth's axial tilt would spend significant time at extreme values, far from the current 23.5 degrees, on timescales of tens of millions of years. The climate changes associated with such tilt variations would be dramatic, larger than any climate change in Earth's recorded geological history. This is the most important thing the Moon does for Earth. Not the tides, not the rotation rate. The stabilization of the axial tilt, keeping Earth's climate system in a regime that has been compatible with complex life for hundreds of millions of years. The Lasker, Jutel, and Robutel 1993 Nature paper, Stabilization of the Earth's Obliquity by the Moon, used a secular perturbation theory to calculate the evolution of Earth's axial tilt with and without the Moon over hundreds of millions of years. Without the Moon, the axial tilt was found to undergo chaotic variations between approximately 0 and 85 degrees on timescales of tens of millions of years. With the Moon, the tilt is confined to the 22.1 to 24.5 degree range. Mars, which lacks a large stabilizing moon, has an axial tilt that varies between 0 and 60 degrees over millions of years, providing an observational confirmation of the theoretical prediction. Stop here. Without the Moon, Earth's axial tilt would vary chaotically between 0 and 85 degrees over tens of millions of years. We know this is real because Mars, which has no large moon, actually experiences this. Its axial tilt varies between 0 and 60 degrees. At 85 degrees of tilt, Earth is essentially lying on its side. The poles point at the sun for 6 months and away for 6 months. If you had to survive on Earth with 85 degrees of axial tilt, somewhere between the poles and the equator, where would you live? Drop your reasoning below. Let's follow the axial tilt instability through its consequences for Earth's climate. The current 23.5 degree tilt varying slowly between 22.1 and 24.5 degrees over 41,000-year cycles, is already responsible for the ice ages. The Milankovitch cycles, the combined effects of axial tilt variation, orbital eccentricity variation, and precession of the equinoxes, drive the approximately 100,000-year glacial interglacial cycles that have characterized Earth's climate for the past 2.6 million years. The small variation in axial tilt over 41,000 years, from 22.1 to 24.5 degrees, a range of only 2.4 degrees, is sufficient to trigger ice ages and interglacials. The difference in insolation, the amount of solar radiation reaching the surface, between maximum and minimum tilt at high latitudes is approximately 25 watts per square meter. This relatively small change in energy input is sufficient, through climate feedbacks, to drive the cycle between glacial periods, with ice sheets extending to mid-latitudes, and warm interglacials like the current one. Now consider what happens when the axial tilt varies not by 2.4 degrees, but by 85 degrees. At low axial tilt, near 0 degrees, the polar regions receive very little sunlight year-round. Ice accumulates at the poles. The ice reflects solar radiation back to space, the ice albedo feedback, which promotes further cooling. Ice sheets expand. The global climate cools significantly. As the axial tilt increases toward high values, driven by the chaotic dynamics of the unperturbed rotational system, the polar regions receive intense solar radiation during their summer. The ice sheets melt, the global climate warms. The loss of ice reduces the albedo, promoting further warming. At very high axial tilt, approaching 85 degrees, the climate system enters a regime with no close analog in Earth's history. The poles experience months of continuous sunlight, followed by months of continuous darkness. The equatorial regions, which at high tilt receive relatively less solar radiation than the poles during their respective summers, experience a dramatically different seasonal pattern. The implications for complex life are severe. Organisms adapted to the climate regime at one axial tilt value are not necessarily adapted to the climate regime at another value, and the variation between 0 and 85 degrees represents the full range from ice world to tilt extreme, that is far larger than any climate variation complex life on Earth has experienced. The adaptation problem is particularly acute for long-lived species, trees, large animals, ecosystems that take centuries to millennia to establish. If the axial tilt changes significantly on timescales of tens of millions of years, the climate regime changes with it. Species that cannot migrate fast enough to track the changing climate zone, or that cannot evolve fast enough to adapt to the new regime, face extinction. The Lasker simulation suggests that the chaotic tilt variation without the moon would be episodically rapid. There would be periods when the tilt changes relatively slowly, and periods when it changes rapidly, driven by resonances with the planetary perturbation frequencies. Rapid tilt changes would produce rapid climate changes. Climate regime shifts on timescales of millions to tens of millions of years. For comparison, the end Cretaceous extinction, which eliminated approximately 75% of all species, including the non-avian dinosaurs, was associated with climate changes operating on timescales of thousands to tens of thousands of years following the Chicxulub impact. Rapid tilt-driven climate changes could be similarly severe in their impact on biodiversity. Without the moon, Earth's climate history would have been characterized by repeated, large-amplitude climate regime changes driven by chaotic axial tilt variation. Whether complex multicellular life, which requires billions of years of relatively stable evolutionary history to develop from simple precursors, could have evolved in such a climate is uncertain. It is possible. Life is adaptable. Extinction is followed by diversification. but the pathway from simple cells to complex animals and ultimately to intelligence may be longer or more torturous or less likely in a world where the climate system undergoes radical reorganization on geological timescales. The moon may be the reason the path was short enough. The relationship between Earth's axial tilt, the Milankovitch cycles, and the ice ages was established by the work of Milutin Milankovitch in the 1920s and confirmed by the analysis of deep-sea sediment cores in the CLIMAT project, 1976, and subsequent work. The 100,000-year glacial cycle, the dominant period in the last 2.6 million years, is thought to be driven primarily by orbital eccentricity variations, amplified by the ice albedo and CO2 feedbacks. The 41,000-year period corresponds to the obliquity, axial tilt, cycle. Spectral analysis of climate proxies from ocean sediment cores confirms peaks at 100,000, 41,000, and 23,000 years corresponding to the three main Milankovitch periods. Here is the detail that most people do not know, and that makes the question of what happens if the moon disappeared more immediate than it might seem. The moon is leaving. Not dramatically, not quickly, at approximately 3.8 centimeters per year, a rate that has been measured with extraordinary precision using lunar laser ranging, which bounces laser pulses off the retroreflectors placed on the moon by Apollo astronauts and measures the round-trip travel time. 3.8 centimeters per year, the thickness of a finger. The moon recedes because of the same tidal interaction that slows Earth's rotation. The tidal bulge that the moon raises in Earth's oceans is carried slightly ahead of the moon by Earth's rotation. Earth rotates faster than the moon orbits. This slightly ahead bulge pulls the moon forward in its orbit, adding angular momentum to the moon's orbit and causing it to move to a higher, larger orbit. The conservation of angular momentum in the Earth-Moon system means that as the moon gains orbital angular momentum, Earth loses rotational angular momentum and slows. At 3.8 centimeters per year, the moon recedes approximately 38 meters per millennium. In 4.5 billion years, the time since the moon formed, it has moved from approximately 20,000 kilometers to its current distance of approximately 384,000 kilometers. That is consistent with a much faster early recession rate. The recession was faster when the moon was closer and the tidal forces were stronger, and a slowing recession as the moon moved further and the tidal forces weakened. The moon will not recede indefinitely. The recession slows as the moon moves further. Eventually, in approximately 50 billion years from now, far beyond the sun's remaining main sequence lifetime, Earth's rotation rate and the moon's orbital period would become synchronized, in the same way that the moon already keeps one face toward Earth. At that point, the tidal breaking stops and the recession stops. But long before that, in approximately 600 million years from now, something specific changes. The moon will have receded far enough that it no longer completely covers the sun's disk during solar eclipses. Currently, the moon and sun appear almost exactly the same size in Earth's sky, an extraordinary coincidence of current orbital geometry, making total solar eclipses possible. As the moon recedes, it appears smaller, and total solar eclipses cease to be possible. They are replaced entirely by annular eclipses, in which the moon covers most of the sun's disk but leaves a ring of the solar corona visible. This is in approximately 600 million years, which is before Earth loses liquid surface water, as we discussed in the video about the sun's death, making this a moot point for any future Earth-based observers. But the recession is happening now. The moon is 3.8 centimeters further from Earth this year than last year. The total solar eclipses that will occur in the next 600 million years are the last ones Earth will ever experience. We are in the window of total solar eclipses. It is closing. slowly but measurably. This makes the question of removing the moon not just a thought experiment. It puts the moon's presence in context. The moon has been receding for 4.5 billion years. Its influence has been changing, slowly, measurably, irreversibly. The stabilizing influence it currently provides to Earth's axial tilt was stronger in the past, when the moon was closer, and is becoming weaker as the moon recedes. The moon is not leaving overnight, but it is leaving. Lunar laser ranging, the technique of bouncing laser pulses off corner cube retroreflectors placed on the moon by Apollo missions 11, 14, and 15 and Soviet Lunokhod missions, has measured the Earth-Moon distance to millimeter precision since 1969. The measurements confirm the recession rate of 3.82 centimeters per year and provide precise values of the tidal dissipation factor Q for Earth's oceans, which governs the rate of angular momentum transfer. The Apollo retroreflectors remain in use today as part of ongoing measurement programs at observatories including Apache Point Observatory in New Mexico and the Observatoire de la Côte d'Azur in France. Let's address the deepest question that the moon's influence raises. Could complex life have evolved on Earth without the moon? The honest answer is, we do not know, and the uncertainty cuts in both directions. The argument that the moon was necessary for complex life rests primarily on the axial tilt stabilization. Without the moon, Earth's axial tilt would vary chaotically. Chaotic tilt variation drives large amplitude climate changes. Large amplitude climate changes may impede the development of complex life by repeatedly disrupting ecosystems before sufficient evolutionary complexity can accumulate. This argument has been made most prominently by Peter Ward and Joe Kirschvink in their 2015 book, A New History of Life, and by David Grinspoon and others working on planetary habitability. It is not universally accepted. The counterargument is that life on Earth has survived dramatic climate changes before, the snowball Earth events of approximately 700 million years ago, during which ice sheets extended to near equatorial latitudes, and has repeatedly diversified after extinction events. Life is more resilient than the moon stability argument implies. Chaotic axial tilt variation would stress ecosystems, but might not prevent the eventual development of intelligence. Just take a different and possibly longer path. There is also the argument that the Lasker simulation, while it shows chaotic tilt variation without the moon, does not necessarily show that the tilt would spend most of its time at extreme values. The simulation shows the tilt could reach 85 degrees, not that it would typically be at 85 degrees. The statistical distribution of tilt values without the moon is uncertain, and there is the observation that Mars, which has no large stabilizing moon, does have an axial tilt that varies significantly. But there is no reason to think this has absolutely prevented life on Mars. Mars's lack of life, if it is indeed lifeless, is more plausibly attributed to its lost atmosphere and magnetic field than to its axial tilt variability. The question of whether the moon was necessary for complex life on Earth is therefore genuinely open. The moon has clearly shaped Earth's climate history in specific ways. Whether those ways were prerequisites for intelligence or merely features of the particular evolutionary path that led to intelligence on this planet is not resolved. What is not open is the empirical question of what the moon does. It stabilizes the axial tilt. It drives the tides. It has been slowing Earth's rotation for 4.5 billion years. It is the source of total solar eclipses, which will cease in approximately 600 million years as the moon recedes beyond the geometric threshold for total coverage. Remove it, and all of these change. The tides reduce to solar only. The axial tilt destabilizes over millions of years. The rotation rate freezes at its current value. The night sky gets darker. The coastal ecosystems are stressed. The long-term climate system becomes more variable. And the question of whether you would be here, whether any intelligent observer would be looking up at the empty sky where the moon used to be, is a question that current science cannot definitively answer. You wake up tonight and the moon is gone. The night is darker. The tides change within hours. Coastal ecosystems are disrupted within days. The lunar tidal braking of Earth's rotation stops. The day freezes at 24 hours and will not lengthen further. Over tens of thousands of years, the axial tilt begins to drift. Over millions of years, it enters the chaotic regime, varying between 0 and 85 degrees, driving climate changes larger than any that complex life has survived in Earth's history. Whether life survives, whether intelligence survives, whether anything looks up at the night sky 100 million years from now and notices that the tilt of the world they live on has been wandering. That is not knowable. What is knowable is this. The moon is currently 384,000 kilometers away. It is 3.8 centimeters further away than it was last year. In 600 million years, it will be too far away for total solar eclipses. In 50 billion years, it would reach a final equilibrium, but the sun will be long dead. The moon is not disappearing tonight, but it has been leaving since it formed, slowly, measurably, relentlessly. The angular momentum it stole from Earth's rotation over 4.5 billion years is gone, transferred to the moon's orbit, irretrievable. You live on a planet that is being slowly abandoned by its moon. The tidal braking is weakening as the moon recedes. The stabilizing influence on the axial tilt is decreasing as the gravitational effect weakens with distance. The moon will not be gone in any human timescale. It will not be gone in any civilizational timescale. It will still be there when the sun's luminosity makes Earth uninhabitable. But it is leaving. And the world it leaves behind will be different from the world it found. The night sky is darker than it used to be. Just not yet by enough to notice. One question. The moon stabilizes Earth's axial tilt. Mars has no large stabilizing moon. Mars's axial tilt varies between 0 and 60 degrees. Mars may or may not have had life. If Mars had complex life 3 billion years ago, when it had liquid water and a thicker atmosphere, do you think the axial tilt variation contributed to its current state? Or is the loss of the magnetic field and the atmospheric stripping by the solar wind a more important factor? Drop your answer below. Planetary scientists genuinely disagree on the relative importance of these factors. Next video, wormholes. What the physics actually says, why they are permitted by general relativity, why the matter required to keep them open violates the weak energy condition, and what happens when you try to use one. The gap between the mathematics permitting wormholes and the physics permitting traversal is larger than most people realize.
See you there.